Greetings, everyone. Welcome to our exclusive Global Leading Voices webinar campaign. We are delighted to have you join us here today. Please be informed that if you have any questions during the presentation, you may type them into the question box in your control panel. The presenter will answer your questions at the end of the presentation accordingly. Now, without further ado, we will turn the time over to our presenter, who will begin shortly.
Hello, everybody. Listening to that introduction about the conference gave me an idea of it would be interesting to be at the conference, and after people learn how to avoid bribery, to try to bribe everybody and see how well it works. But that's not the topic today. Let me see if I can get my slides to work. There. So that you'll know what my own background is, you know who you're talking to, I'll just give you a little bit of an outline. I am a data scientist or data analyst or statistician or whatever word you like to use for those sort of things right now. And that's a relatively new career for me. For the past 15 years, I've been doing process improvement work, and I wrote a book on it and did training and consulting on it. And prior to that, I was an electrical engineer. So I've done all sorts of things. I like to sail a sailboat. I like to ride my motorcycle. I like to fix problems, and I like to work in the garden. And my wife tells me what to do, and I do it. My business, I'm self-employed, and my business is to do both consulting and training in data analytics and process improvement. And I do that for individual people, and I do it for corporations, any place. The individual people I can do one at a time, virtually. Which is very useful because it's hard to get a whole lot of people in one place at one time. And here's a brief list of the things that I train on. The top list is all statistics, software, and all the rest of it is process improvement topics. So let's get on to the topic for today, which is called FMEA. And in the United States, where I am, that's frequently confused with FEMA, which is a government organization that helps people during disasters or after disasters. But in our case, switching those letters around, this acronym stands for Failure Modes and Effects Analysis. So I'm going to describe what that is today and how you can use it. It's basically a tool that allows us to quantify risk. So everything has risk, and every action we take and every decision we make has a certain amount of risk associated with it. And sometimes we just don't think about the risk. Other times it's important to have to study it and use it as one of our decision-making criteria. But assessing risk and putting a number on it is not a very commonly understood thing. So that's what FMEA does. So I hope by the end of this, you'll at least know enough to have a feeling for what it does and when you might want to use it. And there's lots of information about it on the internet and lots of good books about it. But what the tool does is that it asks you to look at potential ways that something could fail, and then to look at the effects of the failures. So what would be the result if this failed? What would happen? And then we make 3 classifications for each one of those failure modes. We assess how severe the results would be. We assess how likely that failure is of occurring, and then we assess how easy it is to detect the failure. So some things are easy to find and some things are not. I call this, most of my work is in the area of data analytics, where we're dealing with hard data. I call FMEA a quasi-quantitative tool, meaning we're going to be using numbers here, but they're not the same kind of measurements as you would get from a tape measure or a scale. On the other hand, it's better than just asking somebody, what do you think? So you've probably all been asked, maybe even by your physician, on a scale of 1 to 10, how bad is that? My doctor likes to do that with pain. If I go in and I have some kind of pain, which I did just recently, I'm doing some construction in my house, and I drove a splinter underneath the thumbnail of one of my thumbs, and it hurt. It hurt a lot, and it started to change colors and swell up. So I went to the doctor, and the doctor said, "How much does this hurt on a scale of 1 to 10?" I hate it when people ask me that question, because my 5 and your 5 may be very different. And so, it's awkward, but they seem to get something out of it, and they don't give me any way of putting that on a scale. So hopefully I'll get my doctor to come to one of these talks someday. But what we're going to identify, prioritize, document the risks, and then once we know what they are and which ones are the worst ones, we're in a good position to make a plan to mitigate those risks. And I know you can't read the details of that little graph in the corner, but the sooner you're aware of a potential problem and fix it, the cheaper it is to fix. That's a very well-known fact, and especially when it comes to things like software, it's very well known, and it's been quantified that if you can fix a potential problem in the concept stage, that's much cheaper than fixing it after you've made the product and shipped it to a few million people, like Microsoft and Apple do all the time, and like the car companies do. So we have these huge recalls where the automotive company has to recall 10 million vehicles because of a problem that they found. Well, had they found that problem earlier, they would have fixed it and avoided that entire recall. FMEA is not a new topic because it's sort of specialized. A lot of people have not heard of it, but it started in the 1960s in the aerospace industry. And then it was adopted by the automotive industry, first by Ford in the US, and then by Ford, Chrysler, and General Motors in the US. And I believe every excuse me, automotive manufacturer in the world uses this right now. It was also adopted as a quality standard by ISO in 1993. So it's been around for a while, has a lot of use. That's why you can find lots of information on it. And as I describe the details of how we do this, you might be concerned that it could become too complicated or take too much time, and that is a concern that people have. But I like to look at the systems as an onion, where I can start broadly, which is the outer layer of the onion, and take a look at the risks associated with the large chunks of the system, and then bear in and look at each one of those systems and focus on it. And it's made up of subsystems, so we can then look at the risks in the subsystems, and we can keep on going until we're down to the component level. Or if we're dealing with a business process, that's the actions that people take. We can start with the behaviors and the policies of an entire organization, perhaps the IT department, or perhaps the finance department, and then of all the sub-departments that are within it, we can do risk assessment of them. And if we start with the details, it gets too complicated too fast, and people give up. Despite the fact that this was started in high-tech equipment systems, right, rocket ships and spaceships and automobiles and that sort of thing, FMEA can be used for virtually anything. So it can be used for products. It can be used for processes in any service industry. It can be used to examine the effects of human behavior in either product use or in a process. It can be used in assembly, in manufacturing, as opposed to the product itself, the way we put the product together. And it can be used in the design stage of a product. So we can use it almost any place. So whenever risk becomes an issue and we have to decide, are we going to go left or are we going to go right, and we look at criteria for how to make that decision, one of those criteria should always be how risky is this decision. And this gives us a way to assess that. So in addition to those benefits of FMEA, it does a few other things. So I don't think I'll talk about all the items on this slide, but because I've mentioned a few of them, but you'll see when I show you a few forms here later on that one of the benefits is that it can provide a record. If we go through this and we keep track of what we do, we can have a good record for how we made decisions, who made the decision, what the decision was. And if it turns out not to be right, or if it turns out to be very good, we don't have to rely on our memory now to know how we did this and how we came to that conclusion. We have good data. We have tracks of where we've been. And it also, that the process of doing this shows us where we should be applying attention, either physical controls if it's equipment, or administrative and management controls if we're dealing with a administrative process. So I'm going to walk you through here the main steps that we take, and then we'll get into details of how we actually do a calculation and do an assessment. So first of all, we have to decide what it is we're going to assess here. So we collect whatever information we have about it, and it's certainly possible that we don't have enough information to do this, but you'll see that as we go along. So we compile our information. If the system is large or complex, we decide what level of detail we're going to do our system, perhaps break it into pieces. We then have to make some sort of flow charts. If it's a process-oriented FMEA, it's important to build a flow chart so we understand how the process works logically. We then determine for each portion of the system, what are the functions of that part of the system? And I'll talk about functions in detail in just a little bit. So what does it do? And then for each one of those, we determine failure modes. So this can be tricky. So it's important to have people on the team who are aware of ways in which things can fail, and some of these are just common sense, and others are very technical. So and they may not be common sense at all. So, but we'll make a list of failure modes, and then once we have that, we'll take a look at if that failure happens, what effect will it have on my system or my customer? And as we're doing that, we can note what the causes of those failure modes are. We may not know, but if we do know, this is a good time to record it, because if we don't record the cause and we knew what it was, later on, somebody's going to have to do this all over again to know what to fix. Then we assign severity ratings for each one of the effects. I'll show you an example of that. We assign a likelihood rating. That's the probability that will happen, that failure will happen. And we determine the ability to detect that failure mode. So detection is important. If something can fail and we don't know that it failed, that's a lot different than having it fail and it's quite obvious that it failed. And once we've done those things, we can calculate a single number that summarizes all of that into a how risky is this system that I just looked at. So whoops, I forgot. I'm not at the end yet. So once we've done that, we'll review the whole thing. We'll take some action. So there's no point in doing an analysis like this unless you intend to do something about it. So, so we'll try to eliminate or reduce the risks of the system, and then after we've taken our actions, we calculate that risk number all over again, and that allows us to tell whether or not we've the work that we did actually reduced the riskiness or not. Some companies use one team to determine the risk, and then once the problems have been addressed and worked on, they use a second team to assess the risk again, because it's very easy for a team to just assume that everything that we did worked and to plug in all the same numbers and come with the same answers and make them all a little bit smaller perhaps, and make it look like everything always worked, and everything doesn't always work. So sometimes this is done with two different teams. For those of you who are in project management and are familiar with the Project Management Institute, a few years ago, when they reissued their body of knowledge for project management, they included risk as one of the chapters. And so on this slide are the processes that, as PMI describes them, for dealing with risk on a project. So this is a little bit different than what FMEA does, and I can't honestly remember if they mention FMEA as a tool in the PMBOK or not, but we can use FMEA to do these things. This shows the ways in which PMI, the Project Management Institute, when they're talking about risk, this shows their impression of how project managers should deal with risk. So from my point of view as an engineer and scientist, I deal with risk by fixing it, by making it go away. But there are other things that we can do, and I laugh every time I see this slide. So one of them is to just to avoid it. I'm not quite sure what that means, but that's what they say. You can eliminate it, and the FMEA approach is aimed at eliminating or reducing risk. You can transfer it, and I find that a humorous thing too. We'll give it to somebody else. Let John have the risk. But in their case, this means buy insurance. We can assume the risk. So I say, well, it's okay. We know that it's risky, but we're just going to deal with it. We're going to just take it. So everything in life has risk associated with it. I can calculate the risk that I'll die if I cross the street, but I want to cross the street, so I'm going to cross it anyway. In that case, I'm assuming the risk. Or I can do something to stop it from happening or to mitigate it. And that's an FMEA approach directly, is to mitigate risk. As far as the very beginning stages of this to gather information, you can read this list as well as I can, so I won't bother doing that, but this is just a list of possible things and possible sources of information that might be useful to have in order to do the FMEA process. And this list would certainly change, and we depending on the sort of thing that we're assessing. So just a list, useful checklist to see does this exist for the process I'm working on, and do I have it, and have I collected it, and do I understand it? And then we make a flow chart. You know what a flow chart is, so I'm not going to show you or talk about flow charts. But one of the reasons of making flow charts is to see how complex the process is and to make a decision of whether or not we should look at it at a very high level or at a very low level. Sometimes looking at a flow chart, especially in a business process, we can narrow in by our experience to a portion of the process where we have a lot of trouble. So maybe we have a lot more trouble with one department and what they do than any place else, so we can make a decision right off the bat that we're just going to take a look at that department and how they work. And this just shows you some other things we do from our flow charts. So, by the way, I don't know what this organization's policy is on handing out slides, and I apologize. I forgot to ask Ardian that question. But when I do presentations, I'm always happy to give a copy of the slide material to anybody that asks, so they can have this information in front of them, and we don't have to labor over it and read it and talk about it while it's on the webinar. And this is a case where that would be useful. Then we live in our scope, so we've talked about our scope. Now, let's get to the details of actually making an FMEA. So what does determining a function mean? So a function is what this item is supposed to do. So we sometimes that's quite obvious, and sometimes it's not quite obvious. In mechanical systems, in electrical systems, and IT systems, the function of each module is usually pretty clear. In business systems, sometimes it's quite vague, and sometimes things that people do in business have no function at all. They're there because they used to be there. The real need for it went away a long time ago, but because of inertia, the company still does those things. So sometimes the purpose of the function is it has no purpose, in which case going through this FMEA process may help us to eliminate some activities from our organization. But as a rule, every part of it has one primary function, and that's the reason that it was done. So it was done. It was made and put there to perform this function. So for an overhead projector, for instance, the function is to project an image. That's the primary function of a projector. There are secondary functions also, and sometimes there are two primary functions, or maybe more than two, but usually just one. A secondary function, by our definition, is something that it does which you would like it not to do. So an adverse effect, like generating heat or consuming power. So those are functions which we're going to see as negative. I want to project an image, but I don't want the projector to get so hot that if I touch it, it burns my skin. And the way we define these functions is with a two-word description. So we should be able to use this words, a verb and a noun, and I'll show you some examples here. The function of an electric motor is to produce torque. It really isn't to make something go round and round. So from an engineering point of view, it produces torque, and if nothing is stopping the thing that it's producing torque with, then it will go round and round. But there are plenty of cases where electric motors are used and the thing does not turn. It still produces the torque. The function of a light bulb is to generate light. Function of a fuel tank to contain fuel, purchase order, authorize a purchase, etc. So if we can nail it down to the simple two-word purpose, it really helps focus our thinking, so we know clearly what this item is doing. And by the way, if we think about some secondary functions here that are unpleasant, a secondary function of a motor might be to produce noise, to produce heat, either one of which we want. Light bulb generates light. It also generates heat. Incandescent light bulbs have been the standard for light bulbs for quite a long time, and they generate much more heat than they do light. I think in the order of 20% of the electricity consumed by an incandescent light bulb becomes light, and 80% of the electricity becomes heat, which is a real problem in large buildings because when you turn the lights on, then a tremendous amount of heat starts going into the building. Now you have to turn on the air conditioning to get the heat out. At least you do here where I live in Georgia, where it's hot. A secondary function of a fuel tank could be to leak. So now that we have our functions, what are some failure modes? So each one of those things is possible to fail one way or another, and we could have multiple failure modes. So we're going to take a look at the failure modes here, and then assume that each one of these failures is going to occur one at a time in order to arrive at our risk assessment. So here's some typical failure cause examples. A document can be out of date. A calculation can be incorrect. An assumption could be wrong. We could order the wrong material, etc. So you get the idea. By the way, while I'm looking at the slide, in case I don't remember it later on, the calculation. So calculations can be wrong, and that's certainly the case. The calculation for this overall risk assessment is nothing but multiplying three numbers together. So it's as trivial a calculation as you can get. And I taught a course a few years ago where part of it was describing FMEAs, and we had a little case study, and we asked them to practice by calculating the FMEAs. The company where I was doing the training produced some software. They were a systems analysis company, and they had their own software package. And one of the things in their software was an FMEA module to do all the things that I'm going to show you here. And I had another piece of software for them to use to do this FMEA. They said, no, we won't use that. We're going to use our own since we do it anyway. So remember, we come up with three numbers and we're going to multiply them together. That's all. It turned out that the people who didn't use their software got the right answer. And this high-tech consulting systems design company got the wrong answer. And we were perplexed, so we dove into what was going on. The head of the software development team for the company was there in the room. He was part of the class. And so it turns out they had incorrectly multiplied the three numbers together. You can't get any simpler than that. So they were incredibly embarrassed. He was, and the president of the company was in the room also. So I felt bad for that poor gentleman. But he kept his job. There's another term that we use when we're talking about failure modes, and that's a potential failure mode. So a potential failure mode is a failure that would only happen under certain conditions. So normally we wouldn't expect that to happen, but if something unusual goes on, then that failure mode could appear. So these are often worth considering, at least thinking about them to make sure we haven't overlooked them. And a really great example that's going on in the United States right now is the hurricane that drove through the center of our East Coast and is now climbing up, about ready to deluge Boston and New York City, and that is the amount of rain. So it's pretty typical in any sort of manufacturing plant or a chemical plant where they have tanks that store hazardous material to build a dike around the tank. You essentially build a wall all the way around the tank so that if the tank were to fail and all that liquid were to come out, the wall is big enough to hold the volume of material that's in the tank. So that's the purpose of that thing. Well, what happens if you have a rain? What happens if you have 100-year rainfall? So normally the worst rain you might get in a year might be 2 inches or 3 inches of rain. So they design these things to handle not only the amount of material in the tank, but also what if the tank happens to break during a very heavy rainstorm? So now there's a lot of water coming into to this dike system. So it has to hold that too. But every so often, every 100 years, and our Weather Bureau calculates 100-year rainfall for every part of our country. What if that happens? Do we have to design the wall to hold 100-year rainfall plus the tank failing? And we don't know yet what has happened in the middle of our country, but the rainfall that just fell in North and South Carolina in the States was considered a 500-year rainfall. So much rain that you would only expect to see that much rain every 500 years. So certainly all of the systems that have to do with things like this probably failed if they were in the areas that got that 500-year rainfall. So that is a potential failure mode. And my guess is there's an awful lot of messy stuff going on up there right now just because of that, because the systems were not designed to handle it. I'll tell you a short story about one of the things I did very early in my career when I was an electrical engineer doing automation systems. I designed automation systems for manufacturers, and I once got the job of designing the system that would sanitize and pump out a giant underground tank. And the underground tank was put in to handle 100-year rainfall. So the dikes around the tanks that held our chemicals would not hold all of the result of a rupture during a 100-year rainfall. And the government, for some reason or other, ordered the company to mitigate that. And one way of mitigating that was to build a giant underground tank. So great big hole in the ground, cover the hole over, put a pump in it, and put a system in it that would neutralize this chemical so that when we pump it out, it would be safe. And the system, the neutralization agent was chlorine gas. I forget what was in the tank, but so my system had to detect that the system was full of water or full enough of water, had to have a way to say, okay, it's okay to drain it, and that was a manual switch that somebody would decide. So we've now filled up this big tank, and now the control system would start pumping it into the regular drainage system. And as it did that, it would bleed a little bit of chlorine into it to neutralize the effect of the pollutant. Well, if you know anything about chlorine, it's an extremely corrosive gas, and it'll rust almost anything. And if I have a system that's only going to work every 100 years, and it's just going to sit there, not really being looked at, I went to my boss and I said, this system will never work, ever. Within 5 years, it'll be rusted. Nothing will work. The sensor won't work. The switches won't work. Nothing will work. You just can't do this. And he said, look, all we care about is that it works when the inspector comes. After that, we don't care if it works or not. So as a young engineer, that was kind of a blow to my feelings that everybody does the right thing. So when we're looking at effects, we want to focus on the customer. and not necessarily the end customer, but the customer of this process step that we have. So what will happen with the at the next downstream point, which may be the customer that buys from us, or maybe another point in our business process or our manufacturing process. So what will they experience when this failure occurs? And we state it in terms of performance. How will that performance be degraded? And here's some typical effects, right? There could be noise, it could go unstable. As a controls engineer, a lot of things, if they didn't work right, could make a control system unstable. And as a person who designed the control system, sometimes I had to design it so that it would be stable even in the presence of upstream failures. And other times we didn't care, right? So we go over budget, the quality's bad, the thing blows up, you know, so that sort of thing. So we decide what the effects are. Now these are important because these effects are going to be one of the things that go into our calculation. So a little earlier I talked about potential causes. So this isn't a formal part of the FMEA, and we don't use it for calculating riskiness, but as long as we're talking about this stuff, we try to record what the causes are if we know what they are, so that later on people have a head start in fixing it. And here's another list that you can't read, but it's a failure causes, some examples of causes. Right? We don't have enough people. There's an error in a mold if it's a molding operation. We don't have enough security. So why did people break into our IT system and steal all of our names and social security numbers and credit card numbers and all that? I know that's one of the things that that this organization deals with. So if that happens, it's going to cause a failure of some sort. Improper permitting, what that means is if I am building something and the state or the city or the country or some government organization requires that I have a permit to build it, and I get the wrong kind of permit, that then causes my construction people to build something that I didn't intend. So that can certainly happen. So all kinds of things could be the causes of the failure. These causes, by the way, are not part of the risk calculation. These causes are things that we can identify while we're going through the FMEA process, so that later on, if we decide to fix any of this stuff, we have a head start, because as long as we're thinking about it, the causes are likely to be obvious to us. The next quantitative thing that we're going to deal with is severity. So here we want to know, we want to assume that the failure happens and assume that that effect. So on the previous slide here, I showed you a bunch of effects. There may be several effects. So every failure could cause several effects to happen. For each effect, we have to apply a severity rating. So some effects may be extremely serious and other effects may not be very serious at all. So we do that. And the only way we can change this is once the system is designed, if that failure happens and this effect is a result of it, the only way to change that is to change the design of the system in the first place. Either so that the effect is mitigated when the failure occurs, or that the failure is less likely to occur. So everyone, so I've mentioned three things that we're going to quantify here. So let me start talking about those. We're going to do all of them on a scale from 1 to 10, just like my doctor did with my thumb. Today it's pretty good. I'd say it's only about a 1 because I've been taking antibiotics. I had this happen once before, just as an aside, and it was a much bigger splinter, and when I went to the doctor then, there was a piece of wood that was visibly sticking out quite a distance, and he looked at it and he said, well, I'm going to have to take that out. He said that wood is one of the materials that a body will not absorb. So if you get foreign substances in your body, the human body will just absorb them and make them go away. Wood is one of the things that does not get absorbed. So if you get a splinter in you, you have to take it out. And he looked at it and said, okay, I'm going to work on this. And he asked me how much pain I was in, and it was a lot. So let's say I told him it was a 6, because he used the 1 to 10 scale also. And then he said, well, it's about to be a 10 because I am going to give you a shot, and the shot's going to be under your thumbnail. And I guarantee you'll never feel anything that's painful again. It really irritated me that he told me that. Had it been a surprise, maybe I wouldn't have reacted so bad, but it was difficult to know that. So here is a chart. So I want you to pay some attention to this chart. So we're going to look at 3 of these charts. This is a chart for ranking the severity of an effect, right? So something has failed, and there is some sort of effect that occurs, and so I want to know how bad is that. And way over on the right, we have a rank from 1 to 10. That's our objective, is to pick a number from 1 to 10. But in the middle, we have a sentence or a couple of sentences of information which describe what a 10 should be. So if you see a 1 is that it has no effect at all, right? A 2 is everything can still work, but there might be some minimal irritating interference, right? So what's a 10? It affects the safe operation of the system without warning, right? An unplanned, unknown, unpredictable explosion. In the city of Boston, in Massachusetts, here, just about a week ago, the gas company was upgrading their gas lines, and they accidentally did something that caused the pressure in the gas lines to go way up for a while. So I don't know what gas line pressures typically are, but whatever it was, they went up a lot. And the gas lines inside the houses are designed to handle gas at the design pressure. And so when this pressure went way up, then a random group of houses had leaks, had gas leaks inside the house. And as a result of that leak, if there also was a flame or a source of heat, then the house blew up. So we had something like 20 houses in the city of Boston, that in this section of the city, that just randomly exploded. I mean, completely exploded, and the house was just turned into a pile of ash, and people died. So it was extremely severe. That would be a 10. So if we were saying, well, what could happen here? The pressure could get way too high. What's the effect of that happening? Unknown, unpredictable explosions and death, right? So that would certainly be a 10. I assume they didn't do that in this case. So let's return to likelihood. So now we know how serious the effect is on a 1 to 10 scale. And well, before I leave that, if we talk at the left, so on the left-hand side, we have just 1 or 2 words to describe the effect. In the middle, we have some more wording that's a little bit more descriptive. And this is a chart that if a group of people is doing this process, we're very likely that it's very likely that the entire group will we'll come to a common consensus about what the rank should be. So if I just ask one person and don't show them a chart like this, their number could be anything. It depends on their personal experience. But if I show this to a group, and then the worst thing that happens is that they end up arguing between two numbers. Half the group thinks it's a 6, half the group thinks it's a 7. There's nothing wrong with saying, let's split the difference and we'll call the ranking a 6.5, so that it doesn't have to be an integer. But this chart is designed to take a group of people and get a consensus ranking without a lot of argument. And it does. I've done this a number of times, and it almost always converges. Works very well. So let's move on to the likelihood of the failure happening. And this likelihood is going to also be a 1 to 10 scale. And here is the chart that we're going to give the team for determining the 1 to 10 scale. So over on the right is the scale. On the left are some words that tell us, describe the failure probability. And since this is a probability problem, then in the middle column here actually is a probability value. So we can make some assessment for what we think. So it's, instead of just all talking, then we can look at this and say, so look what it takes to be a 10 here. Greater than 1 out of every 2 times, which means this thing is going to fail almost constantly. Right? Half the time we use it, it's going to fail. Well, who would ever do that? Who would make something that fails that bad? Well, they wouldn't do it on purpose, but there may be a section of your process where that in fact happens. And remember, we are looking at the likelihood that something would fail. Whoever designed this wasn't thinking about that, and wasn't thinking that failure is going to be highly likely. So it's useful for somebody else to look at that. And look what it takes to be a 1, right? So failure is unlikely to happen. Fewer than 1 out of every 1.5 million times this function happens, will there be a failure? Virtually never. And then in the middle, we have some numbers that are more reasonable. So we can usually take these failure probability numbers and agree on a range. We can get pretty close. Is it going to fail once every 80 times, right? Once every 2,000 times? So we'll use this and come up with a number, which again might not be an integer. So we might split the difference if we argue. And the last thing we need to put a number on is the probability that we can detect it. So this is given that the failure has happened and given that the effect has happened. So we assume that does happen. We want to know, can we detect it, or can the system detect it? Right? Can our process detect it? If I'm making a product, will my system detect it before it goes out the door and we sell it? Or if it's or is it something that we can see, or is it going to be hidden? And let me just let me just make a point here about these numbers. So the too many words on this slide really say that you can't. These 3 numbers that we're going to apply to do our risk assessment are independent numbers. So if you look at the second paragraph here, it says, do not automatically presume that the detection ranking is low just because the likelihood of occurrence is low. So the likelihood of occurrence could be very low. It doesn't happen very often, but it can be very easy to detect, or the other way around. It can be highly likely to happen and virtually impossible to detect. So that they're not really related to each other. That's why we have to analyze them independently. And here's the chart that we use to pick the detection ranking. And over on the right is our 1 to 10 scale. And over all the way on the left is 1 or 2 words that describes how we're gonna describe this. And in the middle is more details. So let's agree on the description in the middle that describes this section, this detection likelihood in this case, and pick a ranking that corresponds with that. A good example of something that's difficult to detect and yet could have life-altering consequences is getting a medicine from your pharmacist. So your doctor gives you a prescription, and you go to the pharmacist, and maybe you have a heart that's every once in a while sort of acting up, and this thing will calm it down and reduce the effects of a heart attack. So you go get the medicine from your pharmacist and take the pill, take the bottle of pills or liquid or whatever it's going to be, and just assume that the pharmacist knows what they're doing and they gave you the right stuff. And you then go home and administer this to you. But there are failure modes in that process, in the pharmacy process. They can give you the wrong stuff, and if you've never taken this stuff before, you may not know that it's the wrong stuff. They may put the wrong material in a bottle where the label is correct. The label says it's what you want, but the wrong stuff is in the bottle. They may give you something that's the wrong strength. So there may be a bunch of strengths. We can say how many milligrams of the active ingredient should be, and the doctor prescribes a 2 milligram dose. Says take one of these a day, and the material comes in doses from 2 to 20 milligrams. 20 looks like 2 if you're really rushing around and you're in a hurry. So the pharmacist gives you a 20 milligram dose instead of a 2, and you immediately have a heart attack. And you aren't necessarily going to know that unless you examine it very carefully and ask questions very carefully. So there's a lot of undetectable errors that happen in the pharmaceutical dispensing process, which is why if you ever look and see how they do dispensing in a pharmacy, if it's a place where you can watch it, then you'll see they go through an awful lot of checks and balances and an awful lot of care. Because the consequences are in many cases debilitating illness or worsening illness. The illness doesn't go away instead of getting cured, or you die. So now that we have those 3 numbers, we can calculate the single number that tells us the risk of this system, and we call it the risk priority number. We use the acronym RPN. And it's simply the product of those 3 values. So the RPN can go from 1 to 1,000. So the lowest value each one can have is a 1. So 1 times 1 times 1 is 1. And the highest value they can have is a 10. So if all of them have a 10, the RPM would be 1,000. So that is the range that we're going to see for our risk numbers. And that by itself isn't going to be extremely useful. We're going to compare that risk number to risk numbers for other things in order to decide what to fix. And so we're going to be looking at this for many things, and we're going to look at many things that could be dealt with. And the RPN value helps us to rank those so we know which ones to work on. And you should work on the ones that have the highest RPN values first. I haven't thought of a better title for the slide, but I'll tell you what it is, and that is that so we're doing an FMEA. So the process of creating the FMEA, how can that process fail? How can we do a bad job of making our doing our FMEA analysis and coming up with our risk assessments. So that's what this is about. And I've seen all of these things happen. So one failure is that instead of assigning a team to do it, is you give it to one person. And if the company doesn't care about this, or they're just cavalier about it, they may even give it to an intern, to a college student who's working there for the summer. It says, here, we need to do this, and everybody else is busy. You do it. So this poor kid has to do this all by himself, and he's not going to do a good job because he doesn't know enough. Another failure mode is you're not really invested in this. You don't want to do it because it's part of your culture to make sure that you have low risk products or processes. Somebody else made you do it, like your customer said, I'm not going to buy from you unless you have an FMEA analysis on this, or the government has a requirement that you have an FMEA analysis done. So again, you yourself don't have an awful lot of incentive to do this because you don't believe in it, perhaps, but somebody made you do it. So you don't usually get a good answer that way. The third one on here is we do it too late, and we've already talked about that a little bit, and that is that if we do it too late, then it's going to be very expensive to fix everything. So if we do it early enough, we have a chance to fix things cheaply. This FMEA document and the resulting papers that come out of it are supposed to be what we like to call a living document. That is, we don't make it once and stick it on the shelf, but we review it periodically to see how it changes over time. So over time, the riskiness of our system or our product should be going down as we apply energy to it. So if we don't review it, we don't revise it, then that's considered to be a failure mode of the failure mode analysis. And the last one is just that we think it's too hard, too complicated. We don't have time for this. The heck with it. We just won't do it. So that's certainly a failure. I'm showing you now a form. Forms aren't very exciting, but I just want to use this to point out a few things. So on the left are the processes that we're working on. The purpose of the process, remember, so might be light bulb. Purpose is to make light. A potential failure mode would be filament breaks. Potential effects, no light. And then we go through this process and say, well, how severe is it? What's the probability of occurring? What's the probability we can detect it? So the colored columns here are where our 1 to 10 values go. And then right after the red one is the RPN calculation. It's just the product of those three. And the information in between is information that we put down if we know it to help people later on fix it, like what's the potential cause, what controls are in place right now to work on this. If you're really doing a good job, you're gonna recommend some actions be taken. So there's you can't fit it in this tiny little box. So these forms are usually bigger than this. So we'll recommend something. We may assign it if the team has the power to assign responsibility. Maybe the manager of this responsible for this process is part of the team. And so when they decide to do something, you'll assign responsibility and put them there. And then the last box on here is what were the results of the work that we did if we decided to do some kind of mitigation. Here's one that's a little bit, if you're, you may be able to see this, but this is just a partial example, and I'll just go through this a little bit in a little bit of detail with just 1 or 2 things so you can get the idea. So this is for a pizza store, and lots of pizza stores in America. Americans love pizza. So the process here that we're looking at, the first one is the process of answering the phone. And there is a specification for answering the phone for answering it by the fourth ring. So if it rings 5 or more times before we answer it, it's considered a failure. So this is a process failure. And by the way, one place where this kind of failure happens all the time are in call centers. So when people call into a call center to get information about their bank account or information about their how to fix something that broke, those call centers frequently have specifications on how long can the phone ring. So what are the effects of a failure, right? What if we don't answer it by the fourth ring? Well, the customer hangs up, customer becomes mad, we lose a sale, we lose future sales because they tell everybody how sloppy we are. So we've got a group of things here which are potential effects. And then this group assigned a severity value. So they chose this to be a 7. And now, what are some of the causes of those failures? And one of the causes is you can't hear the phone. Another one is the phone is too far away to get to it in time. A third one is the staff is all busy doing something and nobody wants to interrupt what they're doing to answer the phone. And so in the blue column here, what's the probability of that occurring, of these failure modes? So there's that we can't hear the phone, that was ranked pretty low, a 3. Usually they can hear the phone. The phone's too far away, they rank that an 8, so they rank that the highest. So that's the most likely thing to happen, is wherever the phone is, we can't get to it in time. And then they rank the people are too busy and just refuse to answer the phone, they rank that a 5. And then what's the probability of detection? Well, I skipped over that current controls, but those are things that they have already done to try to make answering this phone on time easier. So for each one of these potential causes, they have done something. So they recorded what has been done, and then they say, what's the probability we can detect it? Well, let's start with the bottom one. The one with the lowest probability. So, and that is that the people can't be bothered to answer the phone. Just nobody does it. It's real easy to detect that nobody goes over to the phone and picks it up. The 7 here, they rank the worst one for detection to be the phone's too far away. So maybe that's just the team decided that people aren't aware of that as an issue. And so they ranked it a 7. I'm not sure I would have, but that's what they did. And they can't hear the phone, they rank that as a 5, right? And now if you multiply those 3 together, our RPMs are 105, 392, 105. So the biggest one is this one in the middle. So the phone is too far away to get to in time. That by far is the riskiest the riskiest situation here. So if we're going to do anything to make this better, that's the one we should work on. And so this team made a recommendation to buy a wireless phone headset system, and those are very common in fast food restaurants in the U.S. anyway, so that the phone is always on your head. So you don't have to go any place, no matter where you are, no matter what you're doing. Even if you're making change for a customer, you can answer the phone. And if your brain will allow you to do this, you can count out change, hand it to the customer, say, thank you, come again, and also be talking to somebody on the phone. I couldn't do that, but maybe somebody can. And then they made some recommendations, and you can see the recommendation here was to buy a wireless headset, and it was assigned to somebody. And then at the end, later on, when somebody filled in what are the actions that were taken, well, they didn't do anything for the low ones, and they also didn't do anything for the high risk one. They said it was too expensive, and the manager refused to spend the money. He put it in the next quarter's budget. But they did do something up front on this top one, and it looks like what they did was they turned off the music in the ordering area, so the music that the patients hear no longer goes in the ordering area. So it's quieter there, so it makes it easier to answer the phone. So they did something there. All they had to do was turn a knob, and that fixed that. But they fixed one of the lowest priority things, so they didn't do a very good job here. And I'm not going to go through the details of this. If you get a copy of the slides, you can look at this. But this is one for a training center. What are some of the issues, some of the failure modes, excuse me, and the effects and causes, and the 3 1 to 10 numbers are put in, and they determined 3 things that were highest, or higher by a lot than the other ones. So those 3 things are the ones that were going to be worked on. Okay, I'm all done. I'm happy to take questions. Ardian, it's back to you.
Thank you, Bill, for this great presentation. I want to inform you that PCB provides training and certification services for ISO 9001 Introduction, Foundation, Lead Implementer, Lead Auditor, and also Transition. A PCB certificate on these courses will exemplify your dedication in implementing and managing ISO 9001 processes and frameworks, and most importantly, you will be recognized worldwide. Now we'll go ahead and take some time to answer some of the questions regarding today's session. The first question is, so is FMEA methodology different from root cause analysis?
I would say no, it's not. It's just a form of root cause analysis, but it's directed and aimed at risk. So this is definitely one type of root cause analysis.
Okay, thank you. Now, because of the time limitation, we will only answer one more question for today's session. So the question is, can you please elaborate on how FMEA can be applied to the service industry, particularly the provision of third-party audit and certification services? What are the potential failure modes?
Oh my. Well, I guess I could take a shot at that. I don't do auditing, and I'm not in that business myself, but I can give you an example, and maybe that example will help. When I moved to the city where I live right now, which is Atlanta, Georgia, I came here to be the CEO of a software company, and the owner was a venture capitalist, and he told me, I want you to ignore the finances. So this company is on the verge of going out of business. We have not released our software. We have a new software system that we announced 2 years ago, and it still hasn't been released. Our customers are mad. We're risk losing our biggest customers. So your first job is to go around and visit all of our big customers, tell them there's a new dog in town, and you will fix all these problems and convince them to stay. And so worry about the money. And the second thing to do is get that software out the door, fix whatever is stopping them from finishing the software. So I did that. And while I was doing that, I was getting a report out of our finance system called a backlog report. And I didn't understand it. And when I would ask people, what is this report? What is it telling me? Either they didn't know, or I got different answers from different people. But I didn't spend any time on it until we had solved those first 2 critical, let's not go out of business problems. By the time I could focus on finances and money, one of the first things I did was to figure out what this report was. And I got the 3 people who were involved in making it. Now, each of these 3 people did something financially, manipulated some numbers and passed it on to the next one and passed it on to the next one. And I ended up with this report. And I concluded that what the intent of the report was to measure how much work we had sold, how much, and this was a software company, so we sold software and we sold services to install the software. The services were generally more expensive than the software itself. So how much have we sold that we have not yet delivered? And so we still have some more work to go, and so we still have a backlog of work. So they called it the backlog report because this was work that if we just did this work, we get paid for it. Well, what this has to do with auditing is that this report said that we had, this was a company that had about $1 million, I'm sorry, $10 million a year in sales. So it wasn't a big company. The backlog report said that we had $1 million of backlog. So all we needed to do was do that work, and we would put $1 million to the bottom line, which was substantial for a company our size. When the venture capitalist bought this, he hired an auditing firm, one of the big auditing firms, to come in and audit their finances, audit their data, audit their reports, and decide, so he could decide how much the company was worth paying for. And this report was judged to be a good report and an accurate measurement of backlog. And so the owner of this business paid $1 million for that stored up work that we had already sold that we only had to do. Now, I don't know how much he really paid. He probably offered them 50 cents on the dollar or something, but he paid something for that report. What I figured out was that this report was a complete sham by accident. When we would sell a piece of software, the customer would typically give us a purchase order for, let's say, $25,000 worth of services. We would go do the services, we would finish and charge them $15,000, and we were done. But the company, our customer, would then close the project out. But we took the difference between the $25,000 bulk purchase order and the $15,000 that we billed, and that difference of 10 got added to the backlog report. So that's what they were doing without recognizing it. So the backlog report, the real value of how much work do we have that we've sold and can't and haven't collected yet, the real value is zero. So whatever this man paid for this report, he overpaid. Every dollar was thrown down the drain. That was a mistake by the auditing company. So whatever they did to try to figure it out, they made a mistake, and it caused the company to look like it was worth more money than it really was, and this guy was out money. And so I can tell you what the effect was. He sued his auditor for that. I don't know the results of it, but I hope that answers the question at least a little bit.
Yes, thank you, Bill, once again for this great session, and thank you everyone for attending today's webinar. I would like to let you know that this webinar will be recorded and posted on our website as well as on our YouTube channel together with the slides of the presentation. For more information about our webinars, you can visit our website www.pecb.com. Thank you all and have a great day.